Donc, je vous laisse la parole. Vous avez 40 minutes.
Merci.
Okay.
Merci. Malheureusement, mon français, ce n'est pas assez bien de présenter en français. Je suis désolé. But as an American, I have more important things to be embarrassed about, like Donald Trump. I assure you that he will not be the president. Okay? So I'm going to talk a little bit. My talk will be somewhat similar to Nicholas because we're talking about fast reactors here, but this is about the integral fast reactor, which has some very different characteristics. I started this with a book that I wrote and published in 2008. The URL on top, you can download the book for free if you'd like, and it talks a lot about the integral fast reactor. And these slides will be available if you want them. After I wrote the book, the two people who were my main tutors, I'm not a nuclear physicist or an engineer. I was a commercial fisherman, actually, for 20 years. When the people who were directing the project at Argonne National Laboratories found out I was going to write a book about this, they wanted to make sure that it would be absolutely accurate. So they tutored me in reactor design and reactor engineering and physics for about 9 years. And after my book came out, a couple of years later, they decided we should write a book too. So they wrote this book that tells the story about how this reactor was developed, and you can also download that book for free at that URL on the top. What happened was I had found out about the integral fast reactor when I was writing a novel, and when I realized that this fantastic technology existed that could essentially power the whole planet with fuel that we've already got out of the ground for thousands of years, I decided to write the book. And after I wrote it, I got a telephone call and I was asked to send the book to a person in Russia who I didn't know, but it turns out it was Evgeny Velikov, who was the top scientist in Russia, pretty much ran their national laboratories. And he's the one who had started the ITER project. And when he realized the extent that the United States had developed the fast reactor, he realized that he would not live to see fusion providing energy for humanity, but he realized that the fast reactors could. So he decided that he would put a conference together, and they decided to start a think tank. And they asked me to run the think tank, so that's what I do. And this is our think tank. Now, one of the reasons why I wanted to write the book was because of global warming, which in the United States, a lot of people don't believe in it, but we have proof. And like many graphs, sometimes the data gets so small that you can't see it anymore, so I had to stop at 1990.
Now we have to look in.
Now there's a lot of experience with fast reactors around the world, over 350 reactor years of experience. These are the ones, most of them you've already probably heard of. And in the beginning, when the first electricity that was produced from nuclear power was produced from a fast reactor, the EBR-1. And the scientists at that time thought uranium was very rare and that fast reactors would just be the way that everybody would do this in the future. But light water reactors ended up being developed for the submarines, and then they just scaled them up. So, so the utilization of uranium is very poor, and you have to store the waste for hundreds of thousands of years. Whereas with, excuse me, with the integral fast reactor and pyroprocessing, the disposal time is about 300 years. And it's in a form that's ceramic or metal or glass that won't leach into the environment until long after the radioactivity has reduced to below the level of natural uranium. I'm not going to go through every bit of these, but like I say, I'll make the slides available. I can email them to you or whatever, if you wish. So basically, this is the long and the short of it. To run a 1 gigawatt fast reactor, you bring in 1 ton of depleted uranium every year. And that's about 2 milk crates full. So, and depleted uranium is safe enough, you could carry it in, except you can't carry a milk crate full of uranium because it's a half a ton. You have to do it with a forklift or something. But you don't end up with plutonium, with separated plutonium anywhere. And you don't ever have to enrich uranium anymore. So the integral fast reactor project started at what's now called Idaho National Laboratory. It was Argonne National Laboratory West. And they built this reactor in 1964. They fired it up, and they ran it for 30 years. This is a diagram similar to what Nicholas had. It basically shows the simplicity of a pool-type system, which operates at atmospheric pressure and is in a separate structure from the water side of the heat exchanger, so you don't have a problem with water-sodium interaction. Now, when Charles Till decided that he was going to try to solve all the problems associated with nuclear power, he really wanted to use metal for fuel instead of oxide for a number of reasons, safety reasons and economic reasons, and practicality. The problem was that when metal fuel is fissioning, it swells up about 40%. And so when they first started to try it, they would just get maybe 1% burn up, and then the cladding would break. And when he decided that he was going to try to go back and look at this, the fast reactor project at Dounreay in the UK, the people they'd been trying to figure out how to use metal for a long time. And they said, don't bother, we've tried it, you're never going to get it to work. You can't get enough burn up, it's going to break your cladding. And so he decided he was going to still try it. So actually one day, they were sitting around in the office trying to figure out, how can we do this? And somebody said, well, we've got sodium on the outside. We're using sodium because it transfers heat extremely efficiently. So why don't we just make the fuel pins 40% smaller and put sodium inside the cladding? And that way, the heat will be transferred from the fuel pin. And as it swells up, it'll transfer the heat. So you don't have to machine it like you do with fuel pellets, with oxide fuel pellets, where you machine these pellets down to like within microns. This way you could just put in a fuel pellet, say 4 inches, plus or minus 2 inches. It's like extremely simple because it's got all kinds of space in there. And that's an example of one of these breakthroughs that seems so obvious in retrospect. But people had worked on it for years and years and tried to figure this out. So they put the small fuel pins in, they filled it with sodium there, and in the top, there's a gas plenum where the fission gases will collect. And so what happens is the swelling in the fuel is caused by bubbles made by fission gases. And so the bubbles start to leak out into the, what happens is as it swells up, the the sodium that's around the thing is forced up into the plenum. And so the fuel rod is getting larger and larger and larger and coming closer and closer to the outside of the cladding. And after a while, that those little holes, those little bubbles, they start to join and form channels, and then the channels liberate the gas from the fuel pin, and the gas then goes up into the plenum, and the sodium that was forced into the plenum comes down and goes into the holes. So essentially you get extremely efficient heat transfer through the entire process, and it works great. And they did it for a long time. So they built this reactor, and what they wanted to do was to build an integral recycling area. So they just transfer the fuel bundles over to here, and it's a hot cell because it's highly radioactive, and they do the recycling in the associated building. Now the idea is to build power plants with several reactors and a single recycling plant, and never move plutonium. The plutonium is never separated with the pyroprocessing. The plutonium is always mixed with other actinides. But the only time you would ever move the plutonium or the fuel that contains a mix of actinides off the reactor site is if you're starting up another reactor. If you configure the fuel for maximum breeding with the metal fuel, you can get a doubling time of just 7 years. So Hervé's, the paper that we worked on together, talks about a doubling time of what, 15 or 20 years, I think. But if you use metal fuel, you can actually greatly reduce the doubling time. So okay, so they recycled over 30,000 fuel pins using this technology. So you know, I've heard many people say that, well, we don't know how to do this, but we absolutely know how to do this. And when the project was shut down in 1994, it was in its very last stage. The next step was to design a commercial scale recycling plant to recycle this fuel. But at the time, the US was going to put all their spent fuel from their light water reactors into Yucca Mountain. And so the Department of Energy told the people at Argonne, don't design this to recycle oxide fuel, just metal fuel. And so that was the constraints they were working under. And then they shut down the project for political reasons, and they buried it. And the Department of Energy even suppressed the information until I wrote my book, actually. So what you're looking at with the used fuel is a very small amount of plutonium, 1% plutonium, 5% fission products that you want to get rid of. And that's your real waste, but it's not radioactive for that long. So the idea was to design a recycling plant that could handle 100 tons per year. And if you do that, you get 5 tons of fission products that you just have to, I keep hitting the wrong button here, that you just have to store for 300 years, and you can bury it virtually anywhere because, like I say, it won't leach anything into the environment. And you get 2 tons of fuel, and you get 93 tons of depleted uranium, which is easy to store, and we have plenty of it. So about 3.5 years ago, we had a meeting with the Secretary of Energy and proposed that we design this, basically take up where the project left off in 1994, restart the project and design a 100 ton per year recycling facility. And the Department of Energy agreed to do that, and so the first 2 years of the project, we did the conceptual design, and now they're doing the final design, which will be finished next year. And then we'll be ready to build this. And it's very, very simple compared to aqueous reprocessing, which, you know, I'm sure many of you, probably most of you, have been to La Hague and you've seen the huge recycling facility. It looks like a city, but 2/3 of it is underground. This thing, you can put this in almost in a large garage. It's not very big at all. And it'll be quite cheap. But what's really important about, one of the important things about this is it essentially solves the million-year waste problem. Now, those of you who are engineers or scientists or who study these things understand that nuclear waste is really not a problem even the way it is today. There's so little of it. It's easy to store. But it's a public perception problem. So if you want nuclear power to be powering the world, a big part of making the public aware that this isn't a problem is finding a way to solve it. And so this is a logarithmic scale. It's about 300 years by the time you get to the level of natural uranium ore if you recycle it using pyroprocessing. Now, unlike the safety factor of getting your radiation down for the waste, when it comes to the fuel, you want the radiation to be really high because you don't want people stealing it and making it into weapons. So this gives you some idea of the actinide mix that you have for pyroprocessing IFR fuel. You have extremely high radiation, so it has to be, the whole process has to be done in hot cells, and there's no danger of somebody stealing it, taking it out, building a weapon. You can't build a weapon with something that has this much gamma radiation and other types of radiation that it's going to make it impossible to even handle. Now, at the time that this slide was made, it was before we did our project, our conceptual design project for the 100-ton per year facility, and they came up with a number of 400 million. And actually, once they costed it all out in 2015 dollars, that was almost exactly what they came out with. They came out with anywhere from 375 to 450 million dollars. And that's for the first one. Now, if you design this and then you want to build recycling plants to recycle large amounts, you would build essentially cookie cutter operations, because you have the issue of criticality. So you can only do certain size batches, but you can have certain economies of scale by building several of these in the same place. So the cost for the recycling is very minor when it comes to building a recycling center on site where you have the power plant. So in the final years of the IFR project, General Electric put together a consortium of American companies, including Westinghouse and Bechtel, Raytheon, Babcock and Wilcox, and they went up to Idaho National Lab, and they worked with the engineers and scientists there, and they developed the PRISM reactor. And then General Electric has since had a small team of engineers refining the PRISM design since the mid-90s. I call it the best reactor that's never been built. It's got 20 years of engineering work on it since they developed it there. And a lot of times people will say, well, you know, faster, it sounds great, but can you do it fast enough? You know, climate change isn't waiting for us, so what makes you think you can do this fast enough? Well, we saw France do it, go to from 20 to 80% nuclear in 11 years. At the same time, France's electricity demand was rising. It was doubling, so you actually went from 10% to 80% in 11 years. And that was with high pressure reactors where you had to build pressure vessels and all that sort of thing. The PRISM is designed for mass production at atmospheric pressure, so you could definitely do it at least that fast. And I want to thank you in France for showing what can be done. So I spoke with over the years with the engineers who developed the PRISM reactor, and I've asked them, how complex is it to build a PRISM? If you had a factory to mass produce PRISM reactors, how complex would it be compared to building, say, a heavy bomber in World War II? And they always say it's much easier. Well, in 1945, the US built 6,700 heavy bombers in 1 year in one country. And if you built 6,700 PRISM reactors, you would be able to produce as much electricity as the entire world produced in 2009 from all sources. So the idea that you can't build them fast enough is absolutely not true. The bottleneck is the startup fuel. You need fuel to start them. And that's the limitation. So you would want to be building more enrichment plants. If you were going to build these very quickly, you'd want to build more enrichment plants and do it as fast as possible and configure them for maximum breeding so that you could have a 7-year doubling time. As far as fuel availability is concerned, it's really not a problem. The US has probably 800,000 tons of depleted uranium. Russia has almost 1 million tons. France, I believe, has sent a lot of their depleted uranium to Russia. I heard that because I was at a conference in St. Petersburg, and there was an environmentalist there complaining that Russia was taking depleted uranium from France, and that was a bad idea. And I said, well, that's a great idea for Russia. It's fuel, you know. But in reality, there's so much of this around the world that we'll never use it all. Even if we build fast reactors to power the whole planet, long before this is all used up, we'll be running with dilithium crystals or something else. And, you know, we just aren't going to need it. But suffice it to say that there's so much fuel available that you will never have to mine uranium again. There's some more of it. We have several locations like this around the United States, and I'm sure that there are many like this in Russia as well, and in the UK. The UK has enough depleted uranium to power its country for at least 500 years. I don't know what that is. Well, I'm done. That was really fast. Okay. So, would there be any questions or comments or anything like that? This is a little shorter than I thought. Usually I have trouble getting it in an hour, but normally I talk about other technologies besides this. So, I wanted to talk a little bit about the cost of this. General Electric has estimated, they were asked to testify before the Congress about how much these would cost, and the number they came up with was about $2,000 a kilowatt in 2015 dollars. Now, I know that a lot of times companies will say that something is, you know, that they'll give an estimate of a price and it will be wildly below what it actually turns out to be. This has happened in the United States actually with Ariba, which assured the United States that if they built a MOX plant for us at Savannah River to dispose of our weapons-grade plutonium, it would cost $550 million. And it's not finished yet, and the price is about $7 billion and still counting. So you can take cost estimates with a grain of salt, but General Electric has a pretty good record recently in this regard because they built the advanced boiling water reactor. That's the last of the newer design reactors that they built. And they built them in Japan, the first two, Hitachi and Toshiba each built one. And it took 36 and 39 months to build the first of a kind reactors, and they cost around $2,000, actually a little bit less than $2,000 a kilowatt. So, so I believe that their cost estimate is quite credible. They want to build them in the UK because the Nuclear Regulatory Commission in the United States is kind of broken, I would say. When nuclear reactors were first being developed, the engineers and physicists would build the test reactors and they would try them out, and then after they tested them and figured out the design, they would then apply for licensing, and the Nuclear Regulatory Commission would license them. Now the system has been turned upside down, so if you want to build a new reactor, you have to get a license for it before you can build it, and so you can't test it. So we're in a situation where companies have a real hard time starting anything new, even to design an evolutionary step of a current reactor like General Electric recently did with the ESBWR. It's a Generation 3+ light water reactor, and it cost them $1 billion to get it licensed. It took many years, I think almost a decade. And here they're talking about Okay. Here they're talking about trying to license an entirely new type of reactor, and the staff at the Nuclear Regulatory Commission doesn't even have the knowledge to do it. So General Electric hasn't even bothered to apply for a license. But then the UK came up with a problem with plutonium. The UK has the world's largest stockpile of plutonium, about 120 tons, and they want to get rid of it. And so the General Electric made a proposal to the UK to build PRISM reactors. France also, Areva made a proposal to build a MOX plant. Part of the problem with this UK plutonium is a lot of it is old and a lot of it is contaminated. About 25% of it is contaminated with fluorides or iron, and that's very untenable for a MOX system. But the pyroprocessing system is extremely forgiving. You could recycle all of that quite easily. So, so GE did a proposal for the UK, and all right. And the Nuclear Decommissioning Authority didn't want to hear about it. They said, "Oh, you put your proposal in after the deadline." Actually, I had also put in a proposal for a similar thing, and I know it wasn't after the deadline. But what happened was there were a lot of people on the Nuclear Decommissioning Authority that didn't really want to talk about fast reactors. But fortunately, the chief scientist on the Department of Energy and Climate Change in the UK happened to be a friend of mine, and so he helped me get a fair hearing for General Electric, and they were invited to come over to the UK and make a proposal, and the process started then. That was about 3 years ago. And at this point, it looks like the PRISM is probably either the top contender or one of the two top contenders for the solution to the plutonium problem in the UK. Everything's been kind of slowed down because of Brexit and because of the controversy over Hinkley Point. So we've just been waiting and waiting. But now Hinkley Point, just this week, I think, or last week, was finally approved by the new government. So hopefully the UK will get going with some of their other projects and we'll make a decision regarding the PRISM reactor. As far as the time to build it, I was looking at Nicholas's presentation about how soon we can expect to see fast reactors that recycle everything, that recycle all the actinides, and it looked like 2040, and after that. Nicholas is younger than I am, so he's not as anxious. I think I like to do things a little faster. And we are going to be ready to actually build the recycling plant within a couple of years, 2 or 3 years. Because like I say, the design is already done, and the final design is just being finished. As far as building the prism reactors to burn the fuel that you would get with the recycling, General Electric, the engineers there who are in charge of the project tell me that they could build it in about 3 years. So even if they're wrong by a factor of 100%, still it's a lot faster than 2040. So we should be able to do this. Any questions, comments?